Hopefully you can hear me okay. Great. Yeah, so my name is Esterson. I'm at ARC at UCL. Conveniently, you heard about ARC a few hours ago from Jonathan, which is great. So I guess my talk in a way is a bit of a weird angle in that really I'm talking about abstraction, layers of abstraction on top of a underlying compute platform. And given that this is an HPC conference, I think a lot of you will probably be saying, well, I don't actually want layers of abstraction. But I think there's been this kind of interesting theme slightly under the surface of a lot of talks in the past 2 days, which is like, we have this kind of new type of user emerging increasingly frequently, where basically they love Python, they're not so sure how they feel about other programming languages. They probably love Jupyter notebooks. They probably love Google Colab. They probably know how to build Docker files and things like that, but they're not so sure about Slurm and SPAC and that sort of stuff. And really, my position is that we can either cater to those users and give them things which they like and they get on with, or basically they buy a GPU and they sit under their desk. And really, we don't want them to do that, okay? Because if they do that, they buy a whole bunch of, potentially loads of GPUs, and it's really expensive and probably doesn't really get utilized. So we kind of want to encourage them towards central UCL platforms. And the way we do that is by meeting them there to some extent. And a lot of those users, the kind of thing they're interested in broadly, we could call the ML lifecycle, which is why I've put that there. So what is that? I should probably define it. That's not the diagram, that is a diagram, right? Basically, what we're talking about is really only two takeaways from this diagram. One, you have different steps and different types of components, and you kind of want different tools for those different things. And two, I didn't draw it on here because it would just be too messy, but really, in any practical use case, you're hopping around all the time between these different things because you're doing some evaluation, you're thinking it wasn't quite where we wanted to be, and you're going back, right? So two things: one, different tools; two, you're hopping around those tools all the time. So now a kind of another setup slide, and then we're done. Our platform, basically, the key thing to understand about this is that it's a pretty small cluster for now. It's a handful of really good NVIDIA NVLinks GPUs, so 8-way GPU nodes, which are great, but it's not that many nodes. It's interesting maybe to note that we are built on top of a larger UCL, actually ARC and UCL project, which is this sort of UCL private cloud. And that means that we are scalable in terms of both up and down in terms of our compute. And so this is an experimental project, but it may well be orders of magnitude larger in the future. There's no reason to believe that it couldn't be. Okay, what does it do? You've seen this diagram already. Basically, it converts a diagram like that into a practical thing like that. So that is the web UI of Kubeflow. The fact that it has a web UI doesn't mean that you have to interact with it, but it works better for presentations. And basically, each of those green ticks is a container or an abstracted thing a bit like a container. So it could be an MPI job or a deep speed job or whatever. And each of those little directory icons, those are artifacts. So you're outputting artifacts at each stage. They're feeding into future steps. It looks a little bit like that diagram, right? That's kind of the idea, is it's easy to see how somebody could move this kind of abstracted thing, which is in their head and that they want, into an actual practical workflow. Yeah, so how do you submit a job like that? Well, basically, it's Python to submit a pipeline spec. I think we heard earlier that Python is the most used, most understood language among researchers. It's not perfect by any means, but it's pretty good in this case because you really don't care about performance, right? Your pipeline submission script is going to run in a fraction of a second, almost always. Nobody in HPC, I don't think, I hope not, is bottlenecked by the time to run their submission script. And basically, this is over API, so it could either be internal to the cluster or from your local machine. And you're not handling any static creds at all, right? You're logging in with SSO, and once you're logged in, you're just submitting it. That's the idea, and you're just importing a Python package. So this is like the Kubeflow. I should say, by the way, sorry, we are deploying Kubeflow. Most of what I'm talking about here is common across Kubeflow deployments, which is inside Kubernetes. If you're familiar with it, a lot of this will be familiar to you. It's not really talk about the implementation details, but if you're interested in implementation, I'm like always very happy to talk Kubernetes. So do pull me down. Yeah, once you've written your submission scripts, you just execute Python. That's the idea. Okay, so I guess I should jump back and say this workflow we have here is an example just from my like dev environment, but we are outputting some kind of BERT model. Okay, so we've trained our BERT model, we've outputted it, but now like we want to do something with that output. Maybe we evaluate it in here, but we want to do something past that. This is another separate component which allows us to then host this model for inference. But the key thing is we're sharing all the same compute here. We're sharing all the same compute, same authorization. And we're just saying, I've got my output model. And you can see here, like I've said, if you can, you probably can't read this, but it says in the storage URI that I'm putting it at, models slash dash slash my inference model. And basically, that could be an output of my pipeline. So I've output my pipeline, I've written Python, I've submitted it, I've stored an artifact. I'm now pulling it to run for inference. Okay. And this is totally flexible about like compute quotas and things. So here I've got 8 A100s to run this model, but it doesn't have to be that. And I can scale it up or down with no like commitments ahead of time. Okay, so I've trained a model and I've submitted it for inference, but now we have this next step, which is we want to talk to it. So here is like a Jupyter Lab interface. I think this is a thing that a few people have talked about today, but basically researchers really love Jupyter notebooks. And if you can give them a Jupyter notebook on top of an existing platform, they're going to love it. Okay. Whether or not that's a good thing, I don't know, but it is the truth. So here we're talking to that model that we deployed in the cluster. So this is really like a full pipeline. Okay. We wrote some Python that like specified a spec, and that spec would be existing containers that might have Python code, or they might have, C++ or Rust or whatever, and they might be built by us, or they might be built by someone who's given you a magic container to train some part of a model. We've now deployed it for inference, and we're now talking to it inside the cluster. And really, like, all of this stuff was very little friction. And the other thing I guess I should say is that all of this is integrated with external UCL storage. So in this case, maybe we store our model on UCL storage, which is external to this platform, or maybe we save our results there. And like the key thing, I guess I was talking about this idea of convincing researchers not to just buy a GPU and put it under their desk. And the really key thing here is that if you show researchers, here is a notebook, you can attach a GPU, you can talk to your storage, most of the time that will kind of be enough to convince them, don't buy a GPU and put it under a desk. And that's actually it's enough, even if it shouldn't be. And it's a win for us because that means ultimately those GPUs go towards a large centralized cluster that can then do the big, expensive, fun stuff like MPI jobs and deep speed jobs, rather than sitting under a desk and running, Jupyter notebooks. Yeah, so I just wanted to kind of go back to this diagram now that we've talked about these various components and say, hopefully you can see now how they decompose into different elements of our pipeline. So Kubeflow pipelines was the first thing I showed you with the Python SDK and the web UI. And that kind of handles your like foundation training and your fine tuning and your eval loop. You have this purple box, this centralized UCL storage. That's handling your data sets coming in and also out. And then, Kserve, which is the YAML inference service we deployed, that's handling the deployment of services. In this case, it was like a BERT classifier, but really it could be anything at all. I mean, you could pull directly from Hugging Face, or you can write your own custom thing. So basically, if it's an endpoint, you can deploy it using that. And then notebooks, I put in this tiny box for ad hoc testing, but that's like kind of the understatement of the century in terms of how researchers actually use it. They like to do a lot of stuff in notebooks first. Again, regardless of whether or not that's a good idea, fundamentally, like we are willing to cater somewhat to what users want because it means that then we can save this compute for the big expensive stuff. Yeah, and I just want to underline again, all of these are sharing common storage, resource quotas, authorization. It's really important that we do it that way because it means that we don't have to divvy up. Users don't have to know, what do I want ahead of time. And if you recall, when I was talking about that diagram at the start, I said one of the important things is that you can jump around, or rather, that you will have to jump around in order to train your model or to go through this ML lifecycle. And having all of these things in common means that you can jump around faster, right? Like if you had to log in separately to separate things, you would be less likely to do it. If you had to decide ahead of time what your resource split was between inference services and training and notebooks, first of all, you might not know. And second of all, actually, that changes dynamically day to day, right? Like somebody is using all their GPUs for inference, and then they go, no, 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 no. Like we've looked at it. There's something really wrong. We have to go back to a fine tuning step. We had to do some alignment or whatever, right? So you keep all of that flexible, which means really sharing some kind of platform and underlying compute. Yeah, I just want to say quickly, we have users at the moment. It is a small cluster, but they're doing all sorts of interesting things, and we want them doing more interesting things, right? Like we're not particularly opinionated about what people use this for. It's a flexible platform. And we expect and want users to use it for more interesting things in the future. In terms of challenges, there are a whole bunch. Basically, one of the big things is that this is new and different to researchers. And what that really means is that we need good documentation. It's like it's a line in this presentation, but really it could be a presentation in and of itself. I'm sure you will know it's that like everyone, all of us are kind of, I think, guilty of forgetting just how important documentation is. And getting it pitched right is really, really difficult. The other thing is that like users are not Kubernetes experts. We can't expect that of them. So this whole thing is running in Kubernetes. In fact, it's running in like 2 layers of Kubernetes. We don't want them to know that really or think about it. There are advantages that it brings to them if they like Kubernetes. They can do some clever and cool things. They have access to the API server. So actually they have a lot of freedom to do that within some like security ring fencing. But we want that for most users to be totally abstracted away. And part of the benefit of Kubernetes as a framework is like it's really built for those kind of abstractions. Yeah, and I did want to make this final note that like the ecosystem for HPC on Kubernetes really is still developing. And what that means for us in the short term is that we have to do a lot of plumbing and fixing things. We have to like do a little bit more legwork to implement in a way fairly simple things like sensible scheduling, descheduling logic. The other thing I think it's worth saying about that is I guess hopefully some of the people in this room maybe will one day be involved, if you're not already involved in open source for that stuff. I mean, there is the HPC SIG, or sorry, not the HPC SIG, there is the scientific computing SIG and the scheduler SIG and all sorts of things inside Kubernetes. And there are like a huge amount of places to be involved in terms of like meetings and discussions, but also bug fixing and docs and features and all this stuff. There's like a ton of work left to do, and a ton of progress already. It's just like clearly in terms of AI, this stuff is becoming more and more important. More and more people are going to be running heavy HPC style workloads in Kubernetes. There's a huge push to get it like fully shipshape to do that, and we're not actually as close to that as you would think in terms of an ecosystem. Yeah, I would say we still have a huge amount of work to do. The biggest thing really, I think, is more users and talking to those users. Like they're kind of the best type of smoke test you can have. They go and they break things and they try things. So we should get better docs, bug fixing, and performance out of that, right? Like users are going to find bugs. They are going to find places where the documentation is not sensible, and they're also going to find performance bottlenecks. So really our kind of current phase is talking to those users and just like understanding, don't conform to what you expect us to want from you. Instead, just ask for the things you want, and we will try and like accommodate you or at least understand what it is that you really want. I think a lot of the time, like the first time you talk to a user, they're not necessarily going to tell you what they really want. they're going to tell you what they think that you expect them to want, or something like that, if I've got all the layers correct. Yeah, because we're on Kubernetes, there's no reason why we can't expand to more components and more services. There's no reason why we can't build higher level abstractions and integrations. So something that might be cool, for example, is GitHub Actions, right? Like, I think that's a thing that increasingly researchers are using, are interested in. And we have this world where like you merge a PR in GitHub and it goes and runs a job in your cluster. That's kind of cool, I think. I mean, I think it's interesting, the idea that like a user could have a Jupyter notebook and they could go and test a PR to some repo because it like automatically fires a job and then they can look in their notebook at the result of that job. That's actually like a cool workflow thing. And then the other thing, yeah, is that there's no reason why we couldn't be. I mean, these are semi-random examples, but there's no reason why we couldn't link to a cloud provider and then bump up and down, which is kind of more efficient because it means that like your allocation can be better because you can better handle spikes. And then the final thing really that I should say here is just performance. I mean, there's a huge amount of work to do about like scalable performance. We're quite good up to 8 GPUs, which is a lot to some and not a lot to others. So that's like if you're using the 80 gig GPUs, that's 640 gigs of VRAM is pretty good. But obviously for some things, you're talking about massively more than that. We're still figuring out like top level performance for multi-node MPI stuff. Yeah, all of that is coming. The reason I chose this angle is because I thought if I talked about performance, I guess you're all doing that kind of stuff already, and I didn't think it was that interesting. So maybe, hopefully, this angle is somewhat interesting. I mean, I guess I just want to finish by saying, is this an HPC talk? Well, yeah, I think basically like if your definition of high performance is high hardware utilization and fast time to research output, then fundamentally what we are giving users is something which they want to use. And so we can get utilization because we can get people on here and share it basically as an alternative to GPUs under desks, which is like the worst for utilization, right? And then also it's fast time to research output, but because it works and it's intuitive to people. So yeah, to me, it's an HPC tool. But yeah, you make up your own mind. I don't mind. That's me, folks.
Thank you, Andrew. Any questions for Andrew? Did you have a question?
Thank you for the nice talk. I wanted to say that I totally agree about supporting user also in their initial exploratory phase. I think that's something, because there was before or yesterday, I don't remember, someone that was saying developing should not be done in HPC. I disagree. I think really that part on being able to have short round trips is important, and you don't want to dedicate a lot of resources to that, but it's important and it gives the user a lot of usefulness. But I wanted to ask you, have you had issues with security or how you manage the thing? Because in Kubernetes, at least for us, it's more difficult to actually partition or give priority or these kind of things.
Yeah, it's totally more difficult, and I agree. It's like a very important point. So, I mean, we are quite early in terms of security in the sense that, like, I think we understand the places where we need to make improvements. I mean, we believe our cluster is like secure, and what we tell users is, listen, like, if your data is like high security data, don't use our platform at the moment because we're in like an experimental early phase. This is one of those areas where hopefully the ecosystem improves, which is to say, like, Kubernetes security is very, very good if you're using it in the kind of classical way that people expect you to use it, right? Which is mostly your cluster is internal to an organization, and that organization basically trusts the stuff that's being deployed. We're a different case where we actually have people who have access to the API server who shouldn't be treated as fully trusted agents, right? And this is like, I guess security is one of those things where there are like so many layers to it. In terms of the outer layer of like sensible things like, can you spoof and pretend you're another user? The answer is no. In terms of lower layer things, like, I mean, I was talking to another ARC person earlier about things like, do we encrypt data when we send it to the GPU? So if you have root access on the nodes, can you actually look at the stuff in the CPU and GPU? And the answer at the moment is yes, right? Like if you had root access, you could see all of those operations happening. We do want to think about that stuff, and hopefully part of it is us internally thinking about it over the next few months, but also partly, hopefully, some of it is HPC on Kubernetes improving and thinking about some of these problems for us, so we know how to do it ourselves. Yeah.
Any other questions for Andrew? Okay, Andrew Esterson.